Okay, great. So we can see the screen now, and it's wonderful to have Cole Miller with us today. And oh, the screen disappeared. I only see a video.
How about now?
Okay, great. All right, so Cole is going to talk to us about big questions in astrophysics. So without further ado, please take it away.
Yes, thank you very much. I apologize that I'm not there in person, but I'm grateful for the opportunity to talk about big questions in astrophysics related to gravitational waves. And here, as was requested of me, I'm going to be focusing on the relatively high-frequency gravitational waves, such as those that will be detected using LIGO India. And given the excellent set of talks that are going to be coming up, indeed the ones that have also happened, I plan to set the stage for a number of topics that are going to be discussed more fully by others. And I'm also going to talk a little bit more about what we could learn if we're lucky enough to have a galactic supernova. Would be a fantastic multi-messenger source and is something that I hope that we are going to see in our lifetime. So the first thing I'm going to talk about is neutron stars and dense matter. And for each of these parts, I'm going to be listing some of the talks that are coming up that are going to be highly relevant, including the panel discussions. I probably do not need to argue for you why it is that neutron stars are interesting, but I'll do so anyway. Neutron stars represent physical extremes in density, magnetic field, gravitational strength. And as a result, they
Hello,
also are wonderful objects to
your screen is frozen and hello, can you hear me?
Cool. Yes, I can hear you.
So we actually lost you for about 30 seconds. So perhaps maybe a slide or so back.
Yes. What do you see now as my slide?
We see slide number 4, why study neutron stars.
Right. Okay. So I had just been giving sort of the overview, which is to say that I'm going to be talking about a variety of topics. And because there are going to be presentations following mine going into these topics in more detail, I will try to simply set the stage. And I'm also going to talk about supernovae. So neutron stars are remarkable extreme objects in many ways, meaning that they give us frontiers in particle physics, nuclear physics, condensed matter, plasma, hydrodynamics, QED, and general relativity. They are really one-stop shopping when it comes to having a view into the extreme universe. One of the most important problems, as represented by this magnificent diagram produced by Dani Paz at the National University of Mexico, is the giant question mark in the center. What is going on there? And this is of interest because there is matter there in a state which cannot be probed in laboratories and cannot be calculated from first principles because of something called the fermion sign problem. We don't know the composition. Are these mainly nucleons, neutrons, protons, with some electrons and muons? Are there hyperons? Is there free quark matter? Are there phase transitions that occur? So with that in mind, we can think about neutron stars. However, before we do that, I do wish to make a confession to unburden my soul of a sin. And that is that when we talk about neutron stars in terms of dense matter, we typically lure people in by thinking about the composition of core matter, as I just discussed. However, most of the things that we can observe do not directly depend on whether it is, say, free quark matter or hyperons or nucleons, but instead on the equation of state, which for neutron stars is a one-parameter family, the pressure as a function of, for example, the energy density. A possible exception would be the cooling of neutron stars, which depends on transport properties and therefore a bit more on composition, but that's really tough to see. Therefore, we're going to talk about observations that relate to the equation of state, or EOS. And I do want to say, this is my usual plea for people who like to model dense matter. Be an informed consumer, please. These are indirect measurements. In order to construct a model and use reliable data, you have to know what assumptions are being made. There is an understandable tendency to say, here's a published paper claiming the radius of a neutron star. I will fit that into my model. But not all results are created equal. We can think first about the information that we have without using gravitational waves, which is, of course, the focus of the meeting that you have. And some of this information is from nuclear theory. Over the past several years, there has been a rise in the use of chiral effective field theory, which uses the symmetries of QCD and is able to a degree, have an understanding of their own uncertainties. There's also been some motion in trying to understand what we can learn from extending QCD at extremely high densities, like many, many times, tens, hundreds of times greater than that of a nucleus, down to lower densities. I think this is less likely to help, but people are still working on it. From the astronomical standpoint, we have high masses for some neutron stars, which places constraints on the equation of state. We have NASA's mission NICER, the Neutron Star Interior Composition Explorer. Here I lead the group within NICER, which is making measurements of the radius, and I think this has been very helpful. In the future, and by future I mean in the next 5 or so years, the moment of inertia of the faster spinning of the 2 neutron stars in what was a double pulsar system should be able to get the moment of inertia to within about 11%. This is something which is a very exciting possibility. So this is the context we have for dense matter without invoking gravitational waves. For gravitational waves, as all of you know, these come from the motion of mass. And so the bulk of neutron star matter is involved in the production of gravitational waves, especially the core, which contains most of the mass. Now, if you think about what it could inform us about, gravitational waves can tell us about relatively cold matter. We're here, cold means relative to the Fermi temperature of about 10 to the 12 Kelvin. Therefore, if we think about 2 neutron stars spiraling into each other, but before their merger, the matter there is cold. Therefore, if we see some gravitational waves, we can learn about the matter. Or it could be hot matter. For example, just after the merger, we have temperatures that can be several times 10 to the 11 Kelvin, and therefore temperature cannot be ignored. Or the production of a neutron star in a core collapse supernova. Of course, various quantities matter for different gravitational wave observations, whether it's tidal deformability or whether it's some of the other things we've discussed, but all of them depend on the equation of state. This, therefore, gives us the possibility to do self-consistency checks. Now, in terms of the most immediate source of information we have, we can think about 2 neutron stars spiraling into each other. When they are very far apart compared to their own radii, they act like point masses. The gravitational waveform will be pretty much the same as it would be if those were 2 black holes of the same masses. However, when they're closer, then they experience each other's tidal gravitational field and are deformed away from the equilibrium spherical shape. This takes energy. The only source of energy is the orbit. So this changes the waveform, and a more minor effect is that because they're not spheres, their actual stirring of space-time is different as well. And a larger neutron star will be deformed more. As a result, an observation of the gravitational waveform will tell us about the tidal deformability, and that in turn will tell us about the structure of the star. Now, it's been emphasized that tidal deformability by itself is a good measurement, but it is common to try to translate this approximately into a constraint on the radius. For the double neutron star event GW 170817, there is not clear evidence for deformation, and this therefore suggests an approximate upper limit, say at the 95th credibility percentile of 13.5 kilometers or so. So this eliminates the hardest or highest pressure equations of state. But if we want to think about being greedy, which is sometimes a good thing to be as a scientist, what can we get with even more, even future information? As Shamim talked about earlier in his flash talk, we can get information from oscillations in principle. Pre-merger oscillations, the F mode is largely going to tell us the density, which is degenerate with information we have. But if you can get G mode oscillations, this could tell you about structure or transitions within the star. Post-merger oscillations, which are probably going to have to wait until the next generation of detectors, might tell you about hot matter. So these are things that we can look forward to in the future. The second part of my talk, I will mention dark matter. Now, there are going to be talks and panel discussions afterwards. So again, I'm only going to give an overview of this topic. I probably don't need to tell you that there are a number of observations starting in the 1930s suggesting that objects are moving around faster than they could and be gravitationally bound if the only matter is what we see and gravity is Newtonian at that level. Most people think it's dark matter of some sort. And there have been a number of great candidates along the way. Those of you with good memories may recall the WIMP miracle, weakly interacting massive particles, which are supposed to naturally give the observed overall average density of dark matter. However, better observations, better experiments don't really confirm that. So we need to think creatively about the possibilities of dark matter. Now, one of those, which is also going to be discussed further in a later talk, has to do with primordial black holes. This is not the main push that people have made. People tend to think about some elementary particle beyond the standard model. However, dynamically, primordial black holes would work just fine as cold dark matter. In order to avoid other constraints, if you're going to make all dark matter out of primordial black holes, you would need to form them before the era of Big Bang nucleosynthesis, and therefore well before 1 second after the Big Bang. In theory, in terms of production, possibilities run over the whole mass range. However, if you want to make all dark matter out of one mass of primordial black holes, only the asteroid mass range is available, about 10 to the 17 grams to about 10 to the 23 grams. What can gravitational waves do? Well, one thing that they could do is if it happens at some point that there are observations at the high frequency level of, say, less than half a solar mass compact objects, yes, in principle, you could make these non-black holes, exotic objects of the type described yesterday, but it would be most logical, I think, to have these be primordial black holes. Another way that gravitational waves would be able to inform us about dark matter would be tidally. A lot of studies have shown that if you have a certain mass, including dark matter, and then the mass contracts, for example, to form a black hole, dark matter can be pulled in and produce an enhanced density around a black hole. Then, in the same way that neutron stars, which are not black holes, they're big puffy objects by comparison, in the same way that neutron stars can have tidal effects on the gravitational waveform, so too would the cloud be able to do this. And therefore, better and better constraints on the tidal deformability of what we think of as black holes could inform us about dark matter. Yet another qualitatively distinct way in which gravitational waves could be related to dark matter comes from what I think is probably the cool new fad in dark matter, which is to say axions or axion-like particles. So the classic axion is something that solves what is called the strong CP problem, but you can generalize this. These are particles beyond the standard model with extremely low rest masses, such that they can have a Compton wavelength that matches the size of a black hole. And if that happens, then a rotating black hole will undergo a process called superradiance, and a large amount of that energy will go into these axion-like particles, which will then decay and produce gravitational radiation. So not only could you have little bits of gravitational radiation, but you would expect black holes of the matching mass to slow down in the rotation. Yay! Of course, part of the challenge here is that black holes could spin or not spin for other reasons too. So you need to be able to decouple these. But this is at least an interesting possibility going forward. The third thing I'll discuss is cosmography and dark energy. And here again, we have a number of interesting upcoming talks and panel discussions. When I talk about cosmography, I mean the measurement of the universe. And there is no exaggeration in saying that the measurement of the universe has given us profound understanding of science. Think about some of the remarkable things that have happened, from understanding that the Earth goes around the sun instead of the other way around, to the fact that the universe is expanding, to the fact that the universe's expansion is accelerating. These are the sorts of things that affect philosophy and the perception of the general public and not just science. How then can black holes and gravitational waves from them help? So I'll talk about two possibilities. One is the measurement of the Hubble parameter, and the second is the characterization of dark energy, which, let's remember, is just a name that we're giving to what it is that is causing the universe's expansion to accelerate. So let's talk about the Hubble parameter. The Hubble parameter is essentially a relation between the distance to something and its apparent recession speed, where we know in reality it's cosmological expansion. Something that has been put to the headline front of a lot of cosmology is that it has been argued by some people that there is a tension between the measurement of this parameter by different methods. In particular, it has been argued that there is a tension between measurements from the cosmological microwave background and more local measurements. Now, I do want to say that historically, if you go back and you ask about the value of the Hubble parameter, there have been disputes before, quite substantial ones, very nasty ones, in fact. But what has happened in the past always is that it has ultimately been recognized that there have been systematic errors much larger than people understood at the time. My guess is that will happen here too. But if it is not, if it is real, then this could lead to major new physics. This, therefore, is something that is a great lure for these types of studies. If we're thinking about gravitational waves, the advantage is the following. When we think about a standard measurement of the Hubble parameter electromagnetically, because it's speed versus distance, well, the speed comes from the redshift. The redshift is pretty easy to measure if you know the host galaxy. You have a bunch of lines, you match them. People have been doing that for decades, centuries, actually, a century. The distance is usually tough for electromagnetic. You need a standard candle of some sort. But for gravitational waves, if you look at a compact binary merger, then you get a luminosity distance as a product. So what you really need is you also need something which is going to tell you the redshift. And that's not so easy with gravitational waves alone. People have tried to think about ways of doing it, but it's tough. It's easiest if you have an electromagnetic counterpart. Therefore, a double neutron star merger or a black hole neutron star merger where the neutron star is torn apart would seem to be a great option. It has been argued that even if you do not have an EM counterpart, if you have at least a large number of well-characterized double black hole mergers, that you can use the distribution of these on the sky with a combination of the large-scale structure to get some sense of the Hubble parameter. So this is one way that you could do it. What about dark energy? Dark energy, the mysterious majority contributor to the full energy density of the universe. For these, in order to understand whether dark energy is essentially a cosmological constant or whether it has an equation of state distinct from the -1 of a cosmological constant, you need more and more measurements, and you need, in particular, precise and distant measurements. There's a major push in the EM community to do this, especially with so-called type 1a or white dwarf supernovae. However, if you have an electromagnetic counterpart, can identify the host galaxy with great confidence, or you have a gravitational waves that you can see very clearly with extremely high signal to noise. So in lower frequencies, this might be something like LISA or next generation ground-based gravitational waves, then you can potentially have a substantial contribution in this way. One thing to note is that weak gravitational lensing is happening all the time. So this actually can slightly adjust the amplitude that we get and fool us a little bit regarding the luminosity distance. Now, by the way, with dark energy and the Hubble parameter, I do want to have one word of warning to the gravitational wave community. The gravitational wave community, especially with a Hubble parameter, has seemed to be extremely enthusiastic about the idea that their measurements eventually will be the measurements of record, the one that everyone will refer to. The electromagnetic community is doing a lot of work too. They are improving their measurements. I think that from the EM standpoint, a gravitational measurement will be one more as opposed to the standard. There are different perspectives on this. The next discussion I will have has to do with black hole populations. Once more, we have some excellent talks coming up. Here we are in 2025. We are 10 years after the first direct detections of gravitational waves. We now have about 200 announced double black hole events from the LVK collaboration, with probably another 100 to go in the current 04 run. And I think that if you had gone to people before 2015 and you had said, by the time we have 200 events, are we going to know the prime formation channel of these binaries? They would have said absolutely yes. But yes? Okay, we would have said absolutely yes.
Oh, I was
However,
just going to say we lost you for about 10 seconds, but I think it's fine. You can keep going. The slide is still the same.
okay, good. Yeah, thank you. I'm happy to be told about that. And again, this, of course, is part of the reason that it's unfortunate that I wasn't able to make it there in person. The thing is that even now, there is no clarity about what formation mechanism is most important. Prior to the first direct detections, people were mainly talking about two channels: isolated binaries, two massive stars both become black holes in the same system and eventually merge, or dynamical channels in dense stellar systems such as globular clusters or nuclear star clusters, where repeated binary single interactions can eventually produce a merger. Now, there's another channel people are talking about a lot, which is in the accretion disks of active galactic nuclei. But if you talk to people, somebody who likes isolated binaries thinks they can do everything that way. People who like dynamical channels think they can do everything that way. And people who like AGN disks can do everything that way. I will tell you that even before the direct detections, I was going to conferences and I was trying to be annoying. Now, I may have succeeded in being annoying, but I did not succeed in getting people to do what I hoped they would, which is to say, what can your mechanism absolutely not do? Because this is the only way to have something that's genuinely predictive. If a model accommodates all possibilities, it predicts absolutely nothing. So waiting for the result and saying, that's just what I predicted, doesn't count. So I tried to tell them that if they accommodate everything, their model is not falsifiable. However, everyone seemed to recognize that it is not as bad to be unfalsifiable as it would be to be falsified. So new epicycles are being put out all the time. I am disappointed. But how can we actually understand more? One of the things, of course, is that if we look at the distributions of the properties which have been observed from ground-based instruments, well, there are some things that people have looked at. Here is from the most recent LVK paper about the mass distribution, where we see a whole bunch of colors there, and we see the rate, the volumetric rate on the vertical axis logarithmically, and the primary mass on the horizontal axis. And there are different fits you can make. You have to make certain assumptions about the underlying population and so on. But, well, what do we see here? We see something that kind of starts maybe a little low and gets sort of high and maybe has a second bump. But prior to these observations, starting in 1998 with the Bala et al. Paper, there was a suggestion that there might actually be a mass gap between neutron stars and black holes, which would be interesting because it would tell us something about core collapse supernovae and formation, but it may not be there. Then we have the upper mass gap. It is believed that for sufficiently large oxygen cores during that stage of a star's evolution, that there can be an instability which will blow the star completely to bits, leaving no remnant. Therefore, there should be some mass gap, maybe 50 to 100 solar masses, for the masses of a black hole from an isolated binary. However, looking at this, there's no obvious mass gap. What does this tell us? Does it tell us that a lot of those high mass things are formed dynamically with hierarchical mergers? Maybe, but as the information has come in, isolated binary people have come up with clever ways around it. Ways of maybe having extra massive hydrogen envelopes or adjusting the nuclear physics, in particular the C12 alpha gamma to 16 oxygen rate. Maybe we can learn about nuclear physics, but we tangle together a whole lot of astrophysics as well.
Um,
Now, the last part,
Cole, sorry, we lost you now for about 40 seconds. So maybe just the previous slide very briefly. Yeah.
absolutely. What I'm saying here about mass gaps is that one of the things that some of the isolated binary people reluctantly would try to quote unquote predict is that there would be a mass gap between about 50 solar masses and 100 solar masses because of paraproduction supernovae, which would blow things to bits. So, well, I don't see it, but the isolated binary people are very clever and they have come up with ways of maybe filling this in. So the question is, are we going to get enough information eventually to really understand whether there's a drop or any kind of signature that might give us a hint about formation? My last discussion is going to be about supernovae, and in terms of the multi-messenger aspect, there's a talk coming up which may or may not talk about supernovae, but multi-messenger astronomy is a big thing these days. Supernovae, you understand, stars go through a variety of nuclear fusion cycles where they start with hydrogen going to helium, helium to carbon. Eventually, when you form iron, you can get no more nuclear energy and it builds up. And when you get to the Chandrasekhar mass, approximately, careful on that, it collapses. And then a lot of things happen. You have neutronization. The protons and electrons in the pre-collapsed core combine to form neutrons and lead to neutrinos. When you get to high enough density, the neutrinos are trapped. When you get to roughly neutron star density, the core bounces, producing a shock that is stalled and revived by neutrinos. This is an inherently three-dimensional problem requiring general relativity. There's turbulence. You require neutrino transport of all three species of neutrinos. This is fantastically complicated, and it is tremendously multi-messenger. So with that in mind, I'm going to talk now about three aspects of the messenger: electromagnetic, neutrino, and then finally going back to our theme of gravitational waves. These are three of the four messengers from deep space. And the fourth one, cosmic rays, is also produced by supernovae. So this has everything at once. If we're thinking about what we can learn about very dense matter, like nuclear density and beyond, I think that we don't get a lot of unambiguous information from the photons. There are two reasons for this. One is that electromagnetically, we only get a small fraction of the total energy. And most of that is actually kinetic energy from the out. And, and then there's even less than that in prompt photons. Also, because the photons are strongly trapped, basically you need the outflow of matter for photons to start leaving, they are delayed by a fairly long time from the collapse. But maybe people have different ideas about this. So with this in mind, let's instead talk and focus on neutrinos and gravitational waves. For neutrinos, it really has to be a close supernova. The closest one in the last 300 years was in the Large Magellanic Cloud, 50 kiloparsecs away, and we only got 19 neutrinos. Since 1987, detectors have become a lot larger. Super Kamiokande is 100 times the volume of what we had at that time. But even at the Andromeda Galaxy, the closest large galaxy, we would only get about 10 neutrinos. So that's not much. But let's be optimists. Let's say that we actually have a supernova in our own Milky Way within 10 kiloparsecs. Then Super Kamiokande would get 100,000 neutrinos with 0.4 nanosecond time resolution and good energy resolution. What a dream. How fantastic. What could we learn? Well, there are lots of things that we can learn with that many neutrinos. As it turns out, for example, there are three main phases of neutrino emission which tell us different things. I mentioned the early aspect where you have protons and electrons combining to form neutrons and leading to neutrinos. So that's something that maybe gives us 10 to the 52 ergs and lasts for about a second, the collapse time. The neutrinos then get trapped, but when the core bounce shock goes out and it destroys a lot of the heavy nuclei, then the mean free path of neutrinos increases and they are released. This is going to last a short time, maybe 10 milliseconds, and release 10 to the 51 ergs. But then the majority of the energy comes from thermalized neutrinos diffusing out of that proto-neutron star, 10 to the 53 ergs in maybe tens of seconds. All of these will tell us different aspects of the mechanism. It would be absolutely invaluable. But the last of these probably is going to be most informative about dense matter. Now let's go to gravitational waves. As you're aware, if you have a spherically symmetric event, there are no gravitational waves, no matter how violent the explosion or collapse. Therefore, the hope is for large asymmetry. And initially, in the late 1980s, when the idea of large ground-based gravitational wave detectors was being sold, there were some studies suggesting that maybe 1% or even more of the total energy could come out in gravitational waves. But now it's thought that for at least a standard core collapse supernova, it's a very small fraction. This means that in order to see the supernova gravitational waves, we probably need something within 2 kiloparsecs or less, even for design strength advanced LIGO. So with that in mind, I would like to make a personal plea to Betelgeuse. Now, I like Betelgeuse. I like the constellation of Orion. It's been one of my favorites for a long time. However, I think now, Betelgeuse, you can do a great favor to humanity by giving it up. So if you blow up now, when we have our detectors on, it's going to be great. Thanks. Another possibility, if we don't want to destroy Betelgeuse, would be that during the collapse, there could be a hadron-quark transition. Some suggestions are this could lead to extra asymmetry, which could strongly enhance the amplitude. If we're thinking additionally about gravitational waves, supernova simulations indicate that most of the gravitational waves are emitted during the proto-neutron star stage when it's a bit less dense and settling down. So here on the right, we have a paper which was led by Camilo Rodriguez, and this is from a particular simulation showing the frequency of different modes of oscillation as a function of time. The frequencies tend to be going up because the system is settling and becoming denser. So these are mainly where you're going to get your gravitational waves. These can be affected by rotation. They can be affected by sufficiently strong magnetic fields. And when there's the bounce of the core, there's a broadband spike. In fact, it has been proposed that the time evolution of the frequency, such as we see here, can even be informative about transport properties and therefore about composition. And as I mentioned, if we have a sufficiently massive neutron star that there is a hadron-quark transition, then the amplitude could be tens of times larger. And then reaching even a bit further, it is now thought that massive star cores usually don't rotate rapidly. The argument is that there is coupling, perhaps convective, with the outer envelope, which is extending to an AU and is rotating so slowly that when the tiny 1,000-kilometer core collapses, even conserving angular momentum, it basically isn't rotating. But what if in
Could you
some...
please wrap up in a couple of minutes or so, if that's okay?
Yes.
Is that okay, great. Thank you.
This is the next slide is my summary slide. So, but if there is a rapid rotation, then the core could become ellipsoidal and emit a lot of gravitational waves. And this is an idea which was first proposed by Chandrasekhar. And the thing is that the evolution from that point is uncertain. It could be solid body rotation, which could give you a lot of gravitational radiation, but if it's differentially rotating, it'll be much less. So there's a lot of uncertainty here. So indeed, here are my conclusions, and I'll be happy to take questions.
Thank you very much for this wonderful overview with, I think, some very nice touches of humor. So thank you.
Thank you.
Let's see. Are there a couple of quick questions? Oh, there's one online as well. Okay, so I think we'll start first with a couple of questions here, and then we'll take the one online. Who had their hands raised? Yes.
Nice talk, Cole. This is Sukant. My question is about NICER, which you touched upon. You gave a great overview. But I was wondering if you can tell us what's the best you're hoping for from NICER observations in the next some years?
NICER is basically no longer capable of taking additional data. There has been enough degradation over time and specific damage that essentially the data we have are the only data we have. Therefore, it's going to be a matter of doing very careful modeling. And as part of that, I think not only the relatively simplified models we've done before, but trying to couple this with our understanding of the plasma physics of the pulsar process might be able to give us additional information. So it's essentially going to be clear, careful, additional modeling rather than new data that is how we can advance with NICER.
Thank you. Good luck with that.
Thank you.
Hi, Cole. I had a question regarding the dark matter. In one of the slides, you mentioned that the dark matter can be in the form of clouds. I was wondering whether it will be more in the form of clouds or it is more likely to be accumulated at the center. And can we distinguish it in some way, or will it be degenerate with the equation of state itself that we may not ever be able to conclude that dark matter exists in the neutron star as form of cloud?
Yeah, great question. So when I was talking about clouds here, I was thinking about just the idea that you have dark matter and something contracts and takes the dark matter with it. But what you're pointing out is another important way that this might be relevant. For example, if dark matter is particles which are less massive than, say, neutrons, then if you have managed to get your dark matter inside a neutron star, it will puff out and act as a cloud. If you have dark matter which is more massive, then it'll be inside and may affect the structure of the star. There's been some interesting work done using effectively the Tolman-Oppenheimer-Volkoff, the general relativistic hydrostatic equilibrium equation, with two coexisting fluids, standard model matter and dark matter. There are ways that this can affect the structure, and here it would be fairly subtle, but it might come in to details of the tidal deformability.
I wanted to ask a question about supernova. I also talked about these the morning of the first day. I'm also enthusiastic about them as sources. I think the last one nearby was 1987, 38 years ago, and that was in the LMC. So my rough number is once every 100 years. Is that a fair number? And then the other question I was going to ask you is, how likely are we to see these optically as well as in neutrinos?
Yeah, I think 1 in 100 years is very reasonable as kind of a standard historical number. The last one in the bulk of our galaxy was Cassiopeia A. This is something that happened in the 1600s, but it was blocked from view from people at the time because of dust and whatever. So yeah, we can't assume that this is going to happen in our lifetime, but it could. And then in terms of, I'm sorry, the second part of your question was?
Optical and neutrino observation possibility.
Optical. Yeah, I think that it, of course, whether we see it specifically in optical is going to depend on where it is. If it happens near the center of our galaxy, the optical extinction is 30 magnitudes. But EM, yes, absolutely, we're going to see it in EM in some bands. And we might even be able to see things like a shock breakout in X-rays. And here, neutrinos could give us an early warning, tell us that within minutes to hours, we'd better be ready for the neutrinos.
I didn't realize that. I thought neutrinos for sure, but I didn't realize. So it will be visible in X-ray.
It should be visible in at least sufficiently high energy X-rays, yeah. I mean, it depends on which energies. At 1 keV, it's going to be destroyed by the intervening stuff. But if you're talking about tens of keV, it should be able to come through.
Are there all sky satellites that would see that?
There are satellites which could be pointed. So this is where...
That's the trouble. They have to be pointed. So, okay, you need the neutrinos as a trigger.
So neutrinos as a trigger will do it, or if you have, if there are gamma rays that come out...
You have to point pretty quickly after that, though, I guess.
You do. If gamma rays are a possibility as part of the shock, you know, like a little bit of a tail, something like the gamma ray burst monitor from Fermi sees half the sky, so it would have an excellent chance of seeing it soon.
Shantanu, I think you had a question.
Yeah.
I think that will be the last one. Yeah, please go ahead.
So this is just a big picture question. I mean, you mentioned about neutron stars are probes of particle physics. Okay. Now, in my institute, there's no one who works on nuclear theory. There are people who work on particle physics phenomenology. They published into HEP-PH section of archive. So whenever I ask them about neutron stars, they said they're not interested because cold QCT is very difficult. I think even you mentioned that you cannot use perturbative QCT. So my question is, can we learn something about beyond the standard model particle physics from neutron stars? Or put it another way, can neutron stars tell us something about physics beyond SU3 cross SU2 cross U1? Not nuclear physics, just pure particle physics, which can go in HEP-PH section of archive.
That's a good criterion, yes. Well, this, I think, goes back to the issue of dark matter. So neutron stars can be probes of dark matter.
No, not without dark matter. I mean, yes, with dark matter, you can play any games. I mean, just from the structure of neutron stars alone. I just without dark matter.
But it's an interesting question. You asked me about whether it can probe beyond the standard model, but you're not allowing me dark matter. So if we're asking about particle physics within the standard model, then it is going to be a challenge. And that's essentially because the highest densities you get in neutron star cores even probably are not more than 10 times nuclear saturation density. And perturbative QCD becomes high error below about 40 times nuclear saturation density. But could we learn about some of the interaction properties of quarks, color flavor locked compositions, and so on? Yes. So I think it kind of depends on what you consider quarks to be. Are quarks an HEP-TH or not? So a lot of nuclear
FPH,
physicists.
yeah. Or even
Yeah.
HEP-TH, yeah.
Yeah. So if the properties of free but strongly interacting quarks interest your colleagues, then this is one of the places that you are likely to be able to actually have it in the universe. And so the properties of neutron stars should be of interest to them.
Okay, fine. Can I just ask a quick, just one word follow-up, Shashwat?
I mean,
Okay, fine. It's okay.
there's an entire discussion session,
Okay,
and I
fine,
would
fine. Okay.
encourage you to participate in that.
Sure. Okay.
Sorry about that, but
No problem. Yeah.
please do ask in the discussion session, and let's move on to the next talk.